Today we discuss and have the presentation on the realistic simulation and machine learning in power electronics. So I will introduce myself. I am Dr. Bằng Nguyễn. I study my PhD in Clarkson University in upstate of New York, and currently I am a senior researcher in National Renewable Energy Laboratory in Colorado. Um, and with me is the co-chair, Mr. Trung Tính Châu. Can you introduce yourself?
Good evening, everyone. My full name is Châu Trung Tính. I'm from PCMC Love in the Nazarbayev University in Kazakhstan. Now I'm like second year in PhD in robotics. Yeah.
Yeah.
Thank you.
So today we will have two presenter. Um, so first we will have Mr. Mian Lau from Princeton University, and the second we have Arif Noor Rasman. He graduate PhD from. Sorry, wouldn't go too much in detail first. So yeah, Mr. Joe, can you introduce our first presenter, and we can start the first presentation now.
Yeah, sure. Thank you, Mr. Phúc. Uh, uh, I'm like honored to be the chair for the presentation in today's 63rd feedback webinar on the topic uh, realistic simulation and machine learning in power electronics. Our speaker, Mr. Miang Liao, currently he pursuing the PhD in electrical engineering in like Princeton University in USA, one of the top university in the world. Mr. Liao earned his bachelor degree in Virginia Tech in 2020 and completed his master degree in Princeton in 2022. And he now continuing his research on machine learning application in power electronic system. His research like in interests includes the machine learning based control for the power converters, point-to-load converter for integrated system, uh, wireless power transfer for UAVs, and retied three-phase inverter for renewable energy system. And Mr. Liao has been recognized with like several research awards such as like Franklin Undergraduate Research Fellowship, the New Jersey Wind Institute Fellowship, the Rao Timula Best Paper Award in 3D IM 2023, and the Best Presentation Award in IEEE APEC 2024. And in today's talk, Mr. Liao will present on the topic machine learning methods in power electronic application. Uh, this is on like emerging and like high impact area with the AI technique applied to solve the complex challenges in the modern power electronics, such as like non-linearity, uncertainty, or non-behavior. That's hard to handle with the traditional controller. This presentation will cover the core machine learning methods, including like deep learning and neural network, and their integration into the power converter system, and like experimental results on the showing how the machine learning improve the performance, the stability or adaptability of the power electronic, like through selected research assemble. Mr. Liao will demonstrate how the machine learning is shaping the next generation of the power system design and control. Mr. Miang Liao, are you ready?
Yeah, I can share the screen.
Okay, if so, please feel free to share your screen and begin your presentation. Okay, the floor is yours. Thank you.
So you can see my slides, right?
Yeah, we can see.
Okay, sure. So we can start. Yeah, so today I would like to talk about some machine learning methods in power electronics application. I would say like machine learning is a tool, but a powerful tool to solve some complicated problems in power electronics. Yeah, actually, it's simply a tool, but not like a research area. It's just like we miss some problem, and the traditional method cannot solve it, and we want to use the machine learning to try to give it a solution. The big category of machine learning can be divided into two parts, like the supervised learning and unsupervised learning. For the supervised learning, that means that our data are pre-labeled. Like we know what is the ground truth. We know this is what, this is that, this is this, this is that. And in the supervised learning, we also have two categories. One is the regression, one is the classification. Regression is just like for example, we have a power electronic circuit. We put some frequency, duty cycle, phase shift into this black box model. We can get the voltage, power, and current. And for the regression, there's a lot of traditional machine learning methods, just like the linear or regularized regression. And we have the sparse linear regression, generalized linear model, Gaussian process, and definitely the neural network and transformer model. For the classification, it's usually for like the fault detection, arc detection. So your input is like voltage, current, and power. Your output is whether the circuit has some fault or not. And there are also some many traditional machine learning methods for it, like naive Bayes, support vector machine, k-nearest neighbors, decision tree, random forest, neural network. And and for the classification, I just give a very simple example. Like we can use the classification for wireless power transfer for an object detection. Because for the inductive wireless power transfer, especially for this EV application, like if I want to wirelessly charge Tesla's car, we need to prevent there's any metal stuff between the coils. If there are any metal stuff there, it will induce the eddy current and got the fire, got heat up and got the fire eventually. There's a lot of existing methods. They sense the voltage, they sense the impedance, they sense quality factor. Recently, some people just use machine learning try to examine the reflection coefficient variation. So by using the machine learning to train the model with a lot of data, those data include voltage and current without foreign object and with foreign object. By training the model, after you have the new data, like the new voltage and current, the model will tell you if there's any foreign objects there or not. Another big category is the unsupervised learning, where the data are unlabeled. This one usually used for the clustering. We have a lot of traditional methods like k-means clustering, mixed module, etc. For the unsupervised learning, we usually have the method with dimension reduction. The advantage of this is like we can find the most important variables and find the correlation between the variables. For example, you have tons of control parameters, duty cycle, theta, everything for like the multi-level, multi-phase converters. But you don't know which parameter will affect the output most. Like we can use those dimension reduction method, trying to find the most important factor and to eliminate the least important factor. So you can reduce the size of your machine learning model. Let me just talk about the difference between the machine learning and the deep learning. The advantage of those traditional machine learning is just what we talked before instead of the neural networks. They usually have better performance on small data set because you usually define some features by yourself. So it has low cost training process and the model is easier to explain. It's not exactly a very black box. But for the deep learning, you can see the graph. the deep learning belongs to the machine learning. It uses a neural network. It's completely a data-driven method. It will learn the feature by itself through tons of data. So, for example, if we want to do the pattern recognition, the input is like an image of a car. The traditional machine learning method used, for example, the decision tree. So it will have a lot of, you see the parameter here, the time, work bus, everything. So, and the output is like car or not a car. But for the deep learning, you just put the input, goes through a neural network and give you the result. And you cannot explain from any perspective. It's just a pure black box. But the result has been proven that the deep learning or the neural network is much more powerful than the traditional method, and it is scalable. Like right now, we use the ChatGPT, a lot of generative AI tool, and those tools just use billion of parameters and use like also the billion of data to train the neural network, and they result in a very good performance, and they are quite scalable. So what is the artificial neural network? The simplest model is named the feed-forward neural network. It's just like what's shown in the graph. The input, for example, can be some power demand. The output can be some control parameters, such as phase shifts. And the input layer, we have the input layer, output layer, and the hidden layer. Hidden layer is the part to create the non-linearity for this model. So this feed-forward neural network can capture the nonlinear and non-ideal effect in the circuit. And how to do the calculation for this one? Like the neurons in the hidden layer or the neurons in the output layer are based on the same rule. So you will have the weight and bias. Weight is something between the neurons. Bias is the offset of each neuron. So for example, for N1, the output of N1 will equals to like the P1 times omega 11 plus P2 times omega 12, etc. So it will be the summation of this omega times P and plus the bias. And you put all these values into a activation function. Here we use the sigma function as the activation function. You can also use a lot of commonly used one like the ReLU, 10H, and so many different things. But the general idea of this activation function is to introduce nonlinearity because they are nonlinear functions. If you don't have the activation functions, this is just a simple linear matrix and make no sense. And we also need to define the loss function. Loss function is for the training purpose. Like the training direction should be based on minimize the loss function. The mostly used loss function is the mean square error. And here is the forward propagation example. This is the simplest neural network, like a 2 input layer, 2 input neurons, 2 output neurons, and 1 hidden layer with 2 neurons. And here I just give a very detailed calculation for it because I thought the knowing how to calculate it in details is very important for understanding, especially for the neural network training and back propagation. Here is the forward propagation, which is what I just talked in the last slide. And here is the back propagation. Actually, the back propagation training just use a partial derivative and a chain rule. That's what they fundamentally use. I don't explain the details of these calculations through the presentation, but I can share the slides, and people who are interested in learning how to do the training can look through all the steps here. It's very detailed steps. Yeah, so after we learn like the fundamental of the neural networks and like how it works, we can look through some go through some examples of machine learning in power electronics application. So I will go through actually two applications. The first application is more about machine learning control. How can we use machine learning to do the real-time control? The second example is about how can we use the machine learning to do the modeling, to do a very complex power electronics modeling. So the first example is machine learning-based power flow controlling multi-input and multi-output energy system. So to introduce the background for this one, we have a huge energy consumption of the base station. Like when we shift from the 4G to 5G, you need 2 times energy consumption for each base station, and you need 3 times more base stations for the same coverage because of the wavelength difference between 5G and 4G. So the electric grid will need to go through the power inverters to supply the base station. And also there's the like the 5G base station, more like a grid edge tower. It can function as like a energy router to function to like manipulate the power flow between different load and different sources. For example, we have a telecom tower. It gets the power from the grid. It can supply the antennas, which is the most fundamental part of it. It can also accept the power from the PV system, which are the renewable energy. And it can also get a bidirectional power flow from the battery pack. Those battery pack can charge and discharge the EV. And we can also have the cloud storage, like the computing, edge computing, near the telecom tower. So with so many input and output, it's more like a multi-input, multi-output system, very complicated system, just like this. And how can we manipulate the power flow? There's a lot of different ways. The simplest or the traditional ways is we have a DC bus. You have a lot of DC input, you have a lot of DC load, DC power, and we have a DC bus. So all of them will first convert their power through this DC, AC, AC, DC phase to this DC bus voltage, and then do the power transfer, power deliveries through this DC bus. Another way is to do with the AC bus or the AC coupling. So the general idea is like we can use the multi-winding transformer in the middle. We just manipulate the power flow through the magnetic flux. So there's several advantages of the AC coupling. First, you have low power stress. First you will have low power stress because the power will be delivered directly from one port to the other port. It won't go through any other port. It will have low component count. It will have high efficiency, fast dynamic response. But the drawback is the control is so sophisticated. For the DC bus, you only need to stabilize the DC voltage here, and you can put a very big, bulky DC capacitor. But for the AC, like everything is coupled together, like the control is coupled. Like if you change the phase shift, or if you change the duty cycle of one port, all the power flow in other port will be changed. So how can we precisely deliver power is the big question here. We can first look at like this multi-winding transformer modeling. So for the 2-winding transformer, we can model them in this T-type. You will have some magnetizing inductance, you will have the leakage inductance. For the multi-winding transformer, we follow the similar idea. So each port will have, we model them in this star network, and all of them will have this leakage inductance here, and they will have a shared magnetizing inductance. So we give an overview of this. I give an overview of this AC coupled converter. So for a 2-port AC coupled converter system, it's like a dual active bridge converter. or it can be like a series resonant converter, whatever. The equivalent circuit will be like this. So it can have different operating modes, depend on the inductance value and the frequency. So here are the equations of this. If your if the in trapezoidal mode is like if your impedance of the series capacitor is smaller than series inductor, and the waveform will be like a trapezoidal. And if the XC, the impedance of capacitor is similar to XL, it will have a quasi-resonant mode. So this waveform will have a lot of harmonics here. So the resonant mode is like XC equals to XL. That means the capacitor resonant with inductor, and the current waveform will be like a sinusoidal. And for the N-port system, it also has a similar idea. The switch node voltage of each one is like a square wave, and we just give them some phase shift to each other, and we keep the 50% duty cycle on each one for all switches. So we first want to decouple the power flow with the control parameters. So how can we do this? Like previously we see this star model, like everything coupled with each other, and we transform from the star model to the delta model. So we have this extended delta model for power flow analysis. And the power flow at each port will be a summation of the phase shift between this port and all the other ports. How to solve it? For example, if you want to generate a particular power flow at a particular point, you need to give it some arbitrary phase shift. And this phase shift needs to be calculated, like back calculated. There's no explicit equations for it because a lot of summations here. Like you cannot get the equation like theta ij equals to what. So we basically need to use the Newton-Raphson method, which is the iterative method to solve it. But the Newton-Raphson method has some drawbacks. First is like Newton-Raphson method cannot capture nonlinearity and non-ideality in the circuit. And also the Newton-Raphson method cannot work for quasi-resonant mode without explicit equations. Like for trapezoidal mode, we have these equations, but for quasi-resonant mode, it's hard to get the explicit equation because it contains so many harmonics, so many high-order harmonics. And also the Newton-Raphson method cannot give us numerical solutions sometimes. That means the solution may not even converge, which will cause the system to go into the instability. Because for real-time control, you definitely want your solution to be guaranteed. If you have no solutions, like your control will blow up and your system will blow up. So that's why we think about like why cannot use a feed-forward neural network to solve this question. So our required is like the power flow, the precise power flow for each port. We can put them into the input layer, and what we want to get is the control parameters. It's like the phase shift for each port. So we build up this simple neural network and try to see how it performs. So we also have an experimental setup. So here we have 6-port MAB converters. We call it multi-active bridge converters. So we operate in 2 different modes, the trapezoidal mode and the quasi-resonant mode. So the difference between each mode is like we change hardware. For trapezoidal mode, we use 16 microfarad. For the quasi-resonant mode, we use 1.33 microfarad. So the overview of this machine learning controller is like we have 2 stages. We usually have 2 stages. For any machine learning problems, the stage 1 is like how we collect the data. The stage 2 is like how we implement the neural network. So stage 1 is, in this case, stage 1 is like we use the LabVIEW to collect data, and we use the TensorFlow to train the neural network. So these are the data from the real circuit. What we do is like we sweep the phase shift. We put tons of phase shift pairs into our 6-port MAB converter, which is the actual converter on the test bench. And we will get some power flow. And we just collect this phase and power set and put them in the TensorFlow to train the neural network. After we get the neural network, we put them into this AI accelerator for implementation. So in the implementation stage, if we have some targeted power, like we have, for example, some targeted power P1, P2 to P6, it will predict the phase shift we need from the phi 1 to phi 6. And we put this phase shift into the DSP, so it will generate the phase shifted PWM for us. And eventually we will generate the actual power from this phase shifted PWM, and we compare the generated power with our targeted power. And this is the automated data collection system we built. There's a live view. It can record the data and display the data here, and display all the voltage, all the current here. For the neural network training and evaluation, we basically generate 3 data sets. So data set 1 is some pre-selected phase shift and generated power. It's for training purpose. And the data set 2 is also the pre-selected phase and generated power, but with different phase shift. You can see the phase shift is different. So that means we use the data set 2 for the test set. So these are some new data, like the neural network training never see before. Usually for the training part, we have the training set and validation set split by 85% and 15%. Training set is used to train the neural network, train this model, and validation set is to validate the output arrow. And validation set is used to select the best model, because during the training purpose, you will do iterative training, like for many epochs, and you will choose the best epoch, best model from some specific epoch regarding your validation arrow. And the test set is something completely different from the previous 2, and you need to evaluate what's the error from the test set. And this is the experimental 1. So for experimental 2, it's a little bit different. So our data set is some random generated power requirement. It's like the power demand. We just generate some arbitrary power demand and want our converter to follow. So we already have the neural network trained from the dataset 1, and also we will use the NR solver. That is the Newton-Raphson iterative method solver. So with this power demand, we get the phase shift from both methods and put them in the multi-active bridge converter, and eventually we have the generated power. So we need to compare those generated power with the random power demand. So from this experiment, from the results, we can see the experiment 1 is like we increase the number of neurons in the hidden layer. That means we increase the number of parameters in the neural network, and we can see the phase error gradually decrease. For the Newton-Raphson method, we can see the error is here. So this error is much higher than the neural network error. Also for the experimental 2, we also sweep the number of neurons in the hidden layer, and we get the power error here. And the power error increase this because if you increase the number of neurons, the model will overfit. After the model gets overfit, the power will gradually increase. So you need to carefully select how many parameters you want to use for the neural network. If the parameter is too less, you cannot capture the feature of the circuit. But if the neural network is too big, you will easily enter the overfit. There is the power error distribution in experiment 2. The power error would be, for the neural network, it would be more like a normal distribution because your loss function is like a mean square error. And for the neural network, and for the Newton-Raphson method, or the equation-based method, you can see the error is more flat around 0, and it typically just give you large mean error, like the mean absolute error here. And we also did the real-time power tracking in trapezoidal mode. So here you can see like we give it some really random power flow demand. So this red line is the targeted power or the power demand. And after we have a demand, we just calculate how much power we need, how much phase shift we need, and feed this phase shift to the converter, and we get the results. We can see even the 5 neuron network, the neural network with 5 neuron can follow the power demand very well. And we also have the real-time tracking quasi-resonant mode. It's the same thing. Like both methods can track, but the neural network is better. Also, we have the transfer learning method for model initialization. Because getting a lot of experimental data is hard. Usually, you need a big experimental, like automated system to collect the data. So what we do is like we use the theoretical data for pre-training. Theoretical data can be from like the equation, you calculate from equation, or you get from the simulation results. Like this, you have a model in Simulink, and you just run the Simulink to get tons of data. So you pre-train the model. This pre-trained model can capture a lot of features of your circuit, but it still has some error because your actual circuit will have some non-ideality. So you just collect a small amount of experimental data from the real circuit and feed this data to this pre-trained network and fine-tune the network. This will be much better than you just feed this data to some random networks. If you have the same amount of experimental data, the pre-trained network will give you much better results. For example, for the trapezoidal mode, we just take a look at how the error will change with number of experimental data used. So with pre-training, we can see with only 100 data, we can achieve very small error. But without pre-training, we may need like 1,000 or even 3,000 data to achieve the same error rate. It's also the same for the quasi-resonant mode. So I think if the simulation or the equation are possible for you to collect data, it's always good to collect data there. So we just give the conclusion of this application one. We use the machine learning-based control framework for design and test. And this machine learning-based control has higher accuracy and smaller error deviation than the traditional Newton-Raphson iterative method. The machine learning-based control can work for more complicated systems where equation-based method may not work. The transfer learning method is also used to achieve high efficiency, to achieve high accuracy, and reduce the size of the training data. So this is for first applications. Do you have any questions for this? Is there any question? Yeah, if there's no question, I will continue with application 2. So the application 2 is more about the more about the machine learning model for very complicated questions. This doesn't need to be the real time, but we need the output of the neural network to have very good performance. So this topic is mainly about the magnet. Magnet is like what we create for the thing we create for modeling the magnetic colors. We have an open source database for this data-driven magnetic colors modeling. The background is like we use a lot of magnetic components in our converters, inverters, and everything. Typically, those magnetic components like inductor or transformer. They occupy the largest volume. They are the biggest part on the board, which you can see from the circuit board, and they introduce significant power loss, which limits the system optimization. However, when we want to optimize the system, we need to know the exact core loss of it. But usually the core loss modeling is very hard to get. The magnetic core loss from the equations, they are just the area of this BH loop, hysteresis loop, or the integral of this loop. This loop is affected by so many factors. For example, it will be affected by material property, like what material you use. It will be affected by flux density range. It will be affected by frequency, affected by waveform shape, affected by DC bias and temperature. So everything can change the shape of it. After the shape change, the area the BH loop area will change and the loss will change. The traditional way of doing it is use, for example, the Steinmetz equation, which has been proposed over 100 years ago. It uses 3 parameters, and it's basically designed for sine wave, not for like the square wave and other things. In recent years, the Kohler in the ETH, they proposed the improved GSE equations, or the IGSE equations. It still has the 3 parameters, but it can predict core loss of other shape of waveform. Also, we have the improved IGSE, like I-squared GSE. They have the 8 parameters, but it's still not enough. We feel like 8 parameters, 3 parameters, or even 10 parameters may not be enough to capture the characteristic of the magnetic component. And also, if you change the parameter to like 10 or 20 parameters, it's very hard to do those calculations, and it's very hard to do everything. So we are thinking about, can we use the machine learning method to predict the core loss and model the magnetics? So we can feed any arbitrary voltage waveform to it, and we can get a result. With neural network, we can have thousands of parameters to capture the nonlinearity here. We have an open source database, which play an important role in support the data-driven and machine learning-based model. We call it Magnet, and we have a website for it. How can we collect the data? Since data is the most important part, either for the data sheet, either for the database or the machine learning training. We create this fully automated loss data acquisition system with a click of button. So with this system, we can arbitrarily change the voltage waveform with the function generator. We can also change the temperature with this OA bus. We can also inject the DC bias, which is not shown here. Like basically, we can change everything to get data for different material and different frequency, different everything. This is the typical measurement results. So we input is like some voltage to the inductor, and we will get some current for the inductor. And here are sinusoidal waves, square waves, three level square waves. Here is the data sheet, like the core loss versus frequency and the flux density, something like that. And we have around like this is the old slide. So right now we have much more data than this, but it's just to give you a general rule of how we create a data set. And this data set, we create them in a very organized way. So anyone can use our instructions to use this data set for neural network training and other things. For the neural network model, we we can have three kind of model for this magnetic modeling. First is scalar to scalar model for a specific waveform, like the sine wave or triangular wave or square wave. So your input would be frequency, flux density, and the shape. The output will only be a power loss. So this is the scalar to scalar. All of these are just number, like some magic number. Then you can have the sequence to scalar model. The input is like a flux density waveform, like the flux waveform. You will just input each data point, and the output is still the power loss. It's more suitable for the arbitrary waveform. Like you don't need to tell it it's sine wave or square wave or something, or three-level wave. You can put any wave there. And the best model actually is the sequence to sequence model. Our input is the flux density, and our output is the edge. And with this, we can also get the power loss by getting the BH loop. So for the scalar, we just use the feed-forward neural network. Very simple. The input is 3 neurons, the frequency, flux density, and the shape. And the output is the power loss. And we switch the number of neurons in each layer, and we can get different results. As the number of parameters increase, we can see the average error will reduce. Also, we just see the Collos curve predicted by neural network and the actual measurement value. As the number of neurons increase, we can see the prediction accuracy will increase. So, for example, the left one is the neural network with less parameters. You can see the measured result and the prediction result are a little bit off from each other. But the right one, they just captured each other. They just match each other very well. Method 2 is like sequence to scalar. So we use the LSTM neural network for it. The input is the series number. We just fed into the LSTM network, and we can conducting arbitrary waveform prediction. So here is the results. For the method 3, like the sequence to sequence model, we need to use the encoder and decoder for realize this function. Here we show the training process of our sequence to sequence model. So this is, since our output should be the time series H waveform. So we can see with the training continuous, the predicted waveform will be more and more like the measured waveform. And here is the predicted BH loop. So we can see as the training goes on, the BH loop will match the predicted BH loop will match the measured BH loop gradually and very well. And with this very accurate BH loop, we can predict the colors from the area. And method 4, still also the transfer learning. We use the MagNet pre-train generic model. We use a large number of data sets to pre-train a very generalized model for transfer learning. So if we have some new materials, like because there are so many materials of the magnetic components, if we have a new materials, we only need a small scale database and to go through this pre-trained model to get our transfer learning results, transfer learn model. And here is also the result, which has the same thing as I showed before. Like with very few number of data, we can achieve good results. We have this web-based open source platform. The interfaces look like this, and you can just play with it. It's very user friendly. Like you can give it some arbitrary frequency, flux, DC offset, temperature, anything, and you can get the visualized results. And you can predict. You can also predict the loss from the both IGSE and the neural network model. You can simulate the excitation waveform with our Plex engine, like we work with the Plex. So eventually we will put our sequence to STM-based model to the Plex simulation tool. So the conclusion of this application is like we have the fully automated CoLoS data acquisition system, which is important for data generation. We have the large-scale open source CoLoS database. We use different models for this database, like the feed-forward neural network model, AISTM model, sequence-to-sequence model, and we also use transfer learning to get a good result from small data sets. We also build a web-based open source platform for use. And I think that's it. Yeah, thanks for listening. Yeah, if you have any questions, you can ask regarding anything related to the machine learning power electronics applications.
Okay, thank you very much for Mr. Liao for the insightful and inspiring presentation. It was like truly the informative and like open up the new perspective on the AI power design in electronics. And now we would like to open the session for Q&A. If you have any question, feel free to raise your hand or write in the chat box. We invite you to speak. So any question? So we would like to invite Nguyễn Bảo Huy.
Yeah, thank you, Mr. Chairman, and thank you, the presenter, for your very interesting presentation. I'm the lecturer from Hanoi University of Science and Technology, and I'm interested in your method on you use the theoretical data to build the base model, and then use the field of experimental data to fine-tune the model, right?
Yeah, correct.
Yeah, exactly.
The transfer learning.
Yeah. So my question is just, what do you think about using something like reinforcement learning for the pre-training? Because for this method, I understand that you have to pre-calculate a large amount of theoretical data or do a large amount of simulation with the scenarios that you defined. But if you use reinforcement learning, you can let the training method just do the simulation as it defined, and you don't need to predefine the simulation scenarios. You get my point?
Yeah, actually not quite familiar with the reinforcement learning, but I mean the basic idea here is like, because we can generate the theoretical data very easily, like we want to use those theoretical data to build a model which is quite accurate to the real model, and it can capture a lot of features there. That's the general idea of this pre-training here. I'm not sure about how to use the reinforcement learning for this. Can you maybe explain more about like how do you want to do it?
Oh, well, sorry, maybe I didn't hear clearly.
Yeah, can you hear me right now?
Yes, but what's your comment about the method of using reinforcement learning here? It's not suitable, not proper approach.
Because I'm not quite sure about how to use the reinforcement learning for this, because I didn't look into the reinforcement learning. That is more about I think about make the right decision for like the gaming training and something like that. So can you explain more about like what does reinforcement learning can do with these models, with any models?
Well, okay, thank you.
Okay, thank you. The like good question and good answer. So like any question for the speaker? So now Mr. Hồ Phúc Kiều.
Hello, can you hear me?
Yeah.
Thank you for presentation. I'm not working on AI, but I have a question that can we say that in the application one, the neural network always have steady state error?
What's that arrow you mean?
I saw some in the result there is some error of the power.
Oh,
Yeah.
you mean the tracking?
Yeah.
Yeah, that's a very good question. So actually, this tracking error not coming from the neural network output, but coming from the implementation. Because we know the DSP has the resolution. Like when we want to use the microcontroller, it has the phase shift resolution. I use the 500 kilohertz for the switching frequency, and the core frequency of the microcontroller is 100 megahertz. So the phase resolution is like divided by 20, so it's like 1.8 degree. So that means our phase can only be constrained to the nearest 1.8 degree. Like the phase can only be 1.8 degrees, 3.6 degree. So if we predict the phase to be 3 degree, it will be automatically changed to the 3.6 degree. And that's where the error comes from, because of the phase resolution. If the phase can be quite accurate, like the error will be much smaller.
So the main reason is due to the high switching frequency. It's not
due to the high switching frequency. Yeah, not because of the neural network error.
And I saw that are you only changing the power? Do you consider ZBS or lot optimization?
For this one, it's only care about the power flow. It doesn't care about the DVS and the loss. And that's also a good question. Like you can always incorporate what you want into the system. Right now, I'm also developing some method or some model for like the DVS circuit. For the DVS, the general idea is like you can predefine what can create the DVS, what can give you DVS. Like usually, if you want to achieve DVS, you need to change the duty cycle of the circuit. Like after you change the duty cycle of each leg, you can get the DVS. And the way to predefine is like you arbitrarily sweep some data, like sweep some phase shift data, and you will get some results. This result incorporates the power flow information and also the ZVS information. Like some data will give you ZVS, some will give you non-ZVS. So during your training, you will say that you only want to get the ZVS. So you only will consider the result with the ZVS. And the neural network can give you some phase shift pairs and duty cycle pairs, ensure the ZVS and power flow at the same time.
So you can give the requirement, several requirement, right?
You can always give the requirement to it. It fully depends on the data set, but that will just create some difficulty for your data set, because you need to collect the data set and tell it and label the data like ZVS or non-ZVS.
Oh, I see. So in your data, with the one power condition, there is several results, right? I mean, several conditions can achieve same power. So
yeah,
you will give all that data.
That's another very good question. It's like the multi-solution thing. What I can tell is like the machine learning cannot solve the multi-solution things. For example, the simplest case is like if you have y equals to x squared, and you have a y, you want to solve for x, right? If you have y equals to 9, the x can be positive and negative 3. In this case, the machine learning cannot give you the result because it's multi-solution. So usually you need to define the solution space. Like you only define like x should be larger than 0. So the same case here. So for our power demand collection, power demand requirement. So here it's like we have a lot of different power demand, and you need to generate the phase shift, and they are one-to-one mapping. Like some specific power flow can like the specific or like the some power flow, they can only have a specific set of the phase shift. Like this 1-to-1 mapping, there's no multi-solution. And usually for many power electronics applications, we have the 1-to-1 mapping because the data set is defined by yourself. You sweep the data. Like sometimes you sweep the phase shift and you get the power. And usually this phase shift will give you different power flow. If the different phase shift can give you the same power flow, then the system is hard to do.
Oh, I see. In here you already define the condition is 50% for duty cycle for all the switch and only phase shift control. Oh.
Yeah, correct.
So
yeah, sometimes if you change the duty cycle and phase shift together, yeah, you will definitely get the same power flow. But you need to predefine, like you need to give it some arbitrary way to create the data set, so it won't have the multi-solution. Even not even for neural network. For like the equation-based method, you also don't want the multi-solution. You only want one best solutions. Must be one solution which is the best, right? Considering the power loss, considering the efficiency.
So you already predetermine that and you only select one solution.
Yeah, you already select one solution based on your training data.
So how long does it take for this training data?
For this case, it's very short. I just train on the personal computer because we only have one hidden layer here. Like this model is quite simple. You see, we only have one hidden layer with several neurons. It's only take you like 1 minute for training.
I see.
On the personal computer. But if you make it bigger and bigger, for example, in the application 2, like here, for the application 2, it can take you like 1 hour for the training if the model become much bigger. If we have multiple hidden layers and we have so many number of neurons.
Yeah, it just come another question that when do we require multiple layer?
Yeah. So why we need multiple layer fully depend on the data. What you usually do is like you give it some different layers, like you give it 2 layers, 3 layers, and 4 layers to see how the performance looks like. If you give it more layers and your error continuously decrease, that means your layer is not enough. You need to keep giving it. And at some sweet point, after that, your error will increase. That means your circuit is overfitting, and you should stop increasing your layer. You should just go with what it is. So it's more like underfitting and overfitting. If you give it less, it's underfitting. If you give it more, it's overfitting. So usually this is by trial and error. But you will have a sense of the data. Like if the model is very complicated, you usually start with some complicated model. If you think the model is like the simple enough, just like the application 1, I just give it very small number of neurons and just a single layer.
Okay,
and
thank you.
Actually for the machine learning community, they have some automatic tools. Like you just give it data and it will sweep the number of layers for you, sweep the number of neurons, number of layers for you, and it will find the best result for you. Yeah, you don't need to do it by yourself. It's just a tedious process.
Thank you.
Yeah,
thank you for
the main reason why we can't like have some intuitive way to define the number of layers, because it's a pure black box model. Like we know, like we can't explain anything in this model. It's a pure black box. So it's also hard to even explain why this needs 3 layers and why this needs 4 layers. The only thing is like we can compare, like the simple model needs less, the complicated model needs more, but we cannot say why it needs 3, why it needs 4, just by trial and error. Yeah.
I see. Thank you for very nice question answer.
Sure. Any question?
Yeah, I have a question.
Yeah, sure.
Yeah. So in the application too, for example, if we want to estimate the core load for example, a new core material, so what the steps should we do? Should we like take the core material and like try to like get some data from that?
Yeah. So if you have a, like for example, if we get some new materials want to test, we need to put them into our like this automated data acquisition system.
Mm-hmm.
So you can see there's the inductor here, device on the
Okay,
test.
see.
So what do we do is like we put this inductor here, and we just run this automated system to get some small size of data.
Yeah.
And after we get those data, so this data should have a lot of different things.
Yeah.
Like after we give it to it, we will sweep the flux density, we sweep the frequency, we sweep the waveform shape, we sweep the DC bias and temperature, and after that, we put this data through this transfer learning, and we put this small scale database to our generic model, and we do the transfer learning to fine tune the data, to fine tune the model.
Yeah. And
Yeah.
and okay. And then like so I just wonder, for example, if we how to say this. So for example, we test with a certain corsef, but then we use the same material. What would the like not like different corsef, for example, like BQ45 or the T or the U's, is it like still okay?
What do you mean? Can you explain it again?
So I mean that at first we test with like the same core material, but with one certain corsef, right?
Yeah.
And then we use that the same material, but we use that in like different corsef. So I
Oh,
don't
you
know
mean
like
the?
if
Oh, you mean? Oh, I understand. Like the
Mhm.
core itself has some variation, like the
Yeah,
manufacturing tolerance. Yeah, I understand.
yeah.
Yeah, that's a very good point actually. Because when we
Yeah.
do the machine learning training, we will always see that there's some core variation. Like even if you
No,
get
yeah, I didn't mean the core material variation, but I mean the shape of the core. Does it matter here?
oh, you mean the step of the core?
Yeah. Like
Do you mean like the manufacturing tolerance?
no, I mean for example, this is a toroidal core or a PQ45 core or that kinds of different
Oh,
shape.
you mean the
Yeah.
physical shape?
Yeah.
Oh, the physical shape. Yeah. We have the data for different physical shape. Yeah, the physical shape does matter.
But
Because this is
I mean that when
yeah.
you test with just one certain shape, and like how we can like apply that data for different than that certain concept.
Oh, I see. Yeah, so we have performed some analysis on different core. They will have slight difference. So usually, if you want the specific shape, like a toroidal shape, you'd better
Yeah.
marry it with the toroidal shape.
Yeah.
If you want to use the toroidal shape data for like some planar magnetics, it will have some error, but that error is still small. It's not that big.
Okay.
You can still use the data, but the best thing is like the best result is still like you need to use the shape you want to use.
Okay. See. Yeah.
Yeah.
Exact shape will be more accurate. Yeah.
Correct.
Yeah. The
Yeah, because
second question.
theoretically theoretically the shape should not matter so much, because when you see the like the Steinmetz equation or the data sheet, even if you
Yeah.
see the manufacturing data sheet, they will just give you the power loss data sheet, and that data sheet doesn't matter sometimes doesn't matter to the shape. It's just like how much power loss watt per cube, like the cubic meter, right? So usually the volume
Yeah.
matters. Yeah, usually the volume matters. They don't care about the shape. so the shape
Yeah.
doesn't change too much. But it will change the flux, how the flux flow, really the flux flow in these core materials, like how the corner looks like, everything will slightly affect the power loss. Just like when you have water going through some tube, if the shape of the tube is different, like it will change a little, slightly change the like speed of the water, like something like this.
Yeah. Yeah. So another question is about like an extend idea, because like when we design the magnetic, we also like have many questions on like what is the optimal widening, for example, interleaf, or what should we use, like planar transformer or just a normal. So I just wonder, like in the future, what your comments on how machine learning can help us on finding the best magnetic design.
Yeah, actually, there's already many research talking about this. Like, how can you use the machine learning method for design optimization? Some people just use the machine learning to help you design a converter. Like you just give it some specific specifications, like you give it the voltage, current for this converter, size of this converter, and the machine learning model can select the topology for you. It can even select the component value for you, and also it can also tell you what is the size of the inductor. And this is more general thing. And for specific things, like there's some paper talking about how can you use the machine learning to optimize the magnetic design. Like what's the shape of the magnetics, what is the shape, and not shape, but the size of the magnetics, and especially, for example, in buck converter, like if you increase the inductor size, you increase the inductance, and you will have smaller ripple, smaller AC loss, and smaller copper loss, I would say. But you at the cost of more volume, and more volume means more core loss sometimes. So there's a lot of like optimization here, and machine learning actually can do it. There are some people has already done it, I think. And in the future, I think more and more people will try to implement it.
Yeah, I think so. Okay, thank you very much for your answer. Yeah.
So I also want to have like one question,
Yeah, sure.
In your core loss simulation framework, like you use the LSTM, the base model to predict the magnetic like core loss from the excitation waveform, right?
Yeah.
Yeah. So like given the recent like advancement in the large language model for the C1 modeling, like do you think the large language model can like eventually to replace the LSTM in this application? Like if not directly, like could like transformer model like by time series model be more the effective to the handle the complex waveform dependence?
Yeah, you are right. In our latest paper, we use the transformer for this. Yeah. In our latest paper, this is the old paper. Old paper, we use the LSTM, and the latest paper, we use the transformer. And transformer does has better performance than the LSTM. The transformer is the basics of the large language model. Yes. Correct.
Yeah. So now for like transformer model, we have like GPT or GPT-40S is also the good model for like time series reduction. I mean they like very good and in the handle some like time series.
Yes, correct. They are very good in handling time series stuff. Because they always use the transformer. It's very good model because your language model is actually very complicated, like much more complicated than the power electronics model. And they can handle it well. That means, yeah, they can handle the power electronics system well. But they are just, but their large language model are too big, like too powerful for power electronics. Like we usually don't need that many parameters. We just need a much smaller model which can work for our community.
Yeah, so because if we want to deploy in some like large language model, maybe we need to face some any challenge on the like Howard constraint, right?
Yeah, correct.
Yeah. Okay. Are there any additional question for the speaker? So I think like yeah.
I saw that you saw some website. Can you, if you don't
Yeah.
mind, can you some introduce that? What kind of application is it?
Yeah, so this website is like a visualizer tool for everyone, like everyone around the world who can use it to do the magnetics optimization. So usually, so what is shown here is like you can give it some arbitrary waveform. For example, if you design a DAB converter, or if you design something like that, you will definitely have some voltage waveform on your transformer, on your leakage inductance. You can put that waveform shape into this model, and you can tune your frequency to the flux density here, and you can get the core loss value. And with those core loss values, it's easier for you to optimize your hardware design.
Oh,
Yeah, it's like, because if you want to get the core loss for the hardware for your design, it's really hard from the equations. For example, if you usually do the optimizations through, for example, the MATLAB tools, you calculate the power loss of your system. Like you calculate the switching loss, you calculate the conduction loss of the RDS zone, calculate the conduction loss of the magnetics, and something like that. You always add those loss together and get the results. And based on these results, you can try to find what is the highest efficiency point for your converter design. But when you want to use the MATLAB for core loss estimation, we usually use the Steinmetz equation, IGSE, for simplicity, but that one is not that accurate. So the optimization you get is not the actual optimization point. So with this website, you can get the real value you want. You can get the real data, like the very accurate core loss data based on your design. So this is general purpose of this website.
oh, can I have question that in this website, do you provide many material or there is just
Yeah.
limit several material?
Correct. There's a lot of material. I can just show here. Magnet. Yeah,
So
this is the open.
this
This is the open source data set. So actually, it has all the data for the material, and also like people can contribute to this website. Like you can put your data here, and we can verify it. We can verify it. If we think your data is accurate enough, we will like accept your data and just build a website based on your data.
Oh, thank you.
So it will be a community thing. Like the ImageNet is what image processing is like what machine learning AI society they use for their data set. Like they try to recognize the pattern, recognize the image, and they continue to increase more image for their data set to increase the training accuracy. And the same for this idea.
Okay, thank you for it.
Sorry, like could you share more about the training data set like you use for the neural network model? I mean like were it's generated by measurement simulation or you like combination parts of them?
The data set is all by experimental results, no simulation. It's all experimental results. Because it's hard for you to simulate those core loss. Like how can you get the simulation data for it? It's very hard. Typical way is like you can use the the FEM method, like you use the Maxwell to get it. But the Maxwell still needs what they call the Steinmetz equation, those kind of data sheet to create the core loss. So there's no theoretical core loss data usually you just measure the data from the experimental result is the best way to do it. It's the simplest way and the best way.
Thank you for your answer. Are there any additional question from speaker? So I think like once again, like we can like sincerely to thank Mr. Miang Liao for his excellent contribution, and thank you all for your attention and like in taking the question.
Yeah, thank you everyone. Yeah,
Yeah.
hopefully this can generate some new ideas for the machine learning, for the power electronics society.
Yeah, thank you, Mr. Liang.
Yeah, thank you, Mr. Mian.